as we jump into this unit on gas laws, I just wanted to quickly introduce different pressure units and their conversions. So the first one to be familiar with is atmospheres. If you're at sea level under normal conditions, you're under 1 atmosphere of pressure. As you go up, like if you climb a mountain or if you live in the mountains, that pressure is going to decrease. As atmospheric pressure decreases, it becomes difficult to breathe. And so that's why sometimes people become lightheaded or like a little bit woozy when they're at high altitudes. There's just not as much oxygen because of the decrease in pressure. The opposite's true though. Like if you've ever experienced coming off a mountain and then you're going to below sea level maybe, the air will suddenly feel very rich because there's actually more pressure below sea level, and so it becomes so easy to breathe. It's invigorating. Anyways, so 1 ATM, if that changes also, and this is why I say normal conditions or decent weather, if that's changing, then it's an indication that there's some kind of storm system moving in. 1 ATM is equivalent to 760 millimeters of mercury. And this is the one I see most often in the lab. We use millimeters of mercury a lot. And there's a picture of a barometer on your lecture handout. So a barometer is a device, and back in the day, and if you have an old barometer laying around, it probably contains mercury. But the barometer measures the atmospheric pressure. And as the mercury, or if you have a newer version, it probably has ethanol in it, as the liquid inside the barometer moves, they measure the differences in height with millimeters. So that's why this looks like a height unit, because it's literally how many millimeters did the mercury move. I've also seen inches of mercury. Don't let that trip you up. You just have to convert from millimeters to inches if you want to do that conversion. It's just measuring the movement of the liquid. The next one is the torr. So 1 millimeter of mercury is equivalent to 1 torr. Little bit ridiculous. It does honor the inventor. It was an Italian physicist and mathematician who invented the barometer, or came up with the idea of it in 1644. So that honors Torricelli. I don't know how to say that. So that honors the Italian physicist. And the other thing about the barometer, which I find really fascinating, we're talking about old school barometers. Before the Weather Channel, before we had like the internet and you could just Google the weather or whatnot, the barometers are really important, especially in parts of the country where people had to be on the lookout for tornadoes and stuff, or hurricanes, right? So a lot of people, a lot of older people had barometers. I mean, a lot of people who are older today might still have barometers hanging in their garages or whatnot, because that was the way you would tell that something's going on in terms of the weather. I digress. Because 1 millimeter mercury is equal to 1 torr, then we see these two very similar relationships. 1 atmosphere then is equal to 760 torr. Last one, you may have seen this. This is pounds per square inch. It's commonly used on tires or like basketballs and stuff too. They have certain PSI requirements. So 1 ATM is around 14.7 PSI, just in case you had to convert between those two systems. Alright, let's do these conversions. They're going to look super similar to the conversions that we set up earlier in the course. So I'm going to start with 652.5 millimeters of mercury. And I want to think about, what am I trying to get rid of? Well, I'm trying to get rid of millimeters of mercury. And in my first one, I would like to go to torr. So I'm going to grab the values in the conversion factor. So 1 millimeter mercury is equivalent to 1 torr. Units cancel. And it's not a very interesting result here, right? Same value for that one. Let's do the ATMs. So 652.5 millimeters of mercury. Trying to get rid of millimeters of mercury. And I would like to go to ATMs, or atmospheres. So my conversion factor tells me that 1 ATM has 760 millimeters of mercury. So I'm going to take 652.5 and divide it by 760. And when I did that, I got 0.8586. So it's pretty cool to think about that lowest pressure ever in terms of ATM. Just to get an idea of how low does it actually go. Let's do PSI, that's the last one. I'm going to start it the same way, 652.5 millimeters of mercury. I want to get rid of millimeters of mercury. And looking at all the information we have currently, obviously you can Google some and find different ones, but I don't have a direct route between millimeters of mercury and PSIs. So I'm going to go millimeters of mercury to atmospheres, kind of repeat what I just did. And then I can go from atmospheres to PSIs. One atmosphere has 14.6959 PSI. So I grab the number from up there. 4 sig figs. So I'm going to report this as 12.62 PSI. Today we're going to start a discussion of the simple gas laws. There's quite a few of them, and they all have different equations, but they tend to be very, very intuitive. So don't let the fact that there's so many different versions stress you out. The first one that I want to discuss is known as Boyles Law. Boyles Law relates pressure and volume. So as I was saying, this is probably a relationship you're already familiar with. If you're the kind of person who tends to overpack when you take a trip, right? Have you ever resorted to sitting on the suitcase in an attempt to get it closed? Well, by sitting on the suitcase, you've increased the pressure on the suitcase with the hopes that the volume of the close will decrease. When you use a sponge, the sponge has a certain volume. And then when you go ahead and squeeze the sponge, now the volume decreased, in this case, to about 1/3 of what it originally was. You release the pressure on the sponge, which decreases pressure. Now volume went back up again. So pressure and volume are indirectly related. They go in opposite directions. When one goes up, the other one goes down. We have a formula to describe this relationship. It's P1V1 equals P2V2. Now I know I gave some analogies or examples from day-to-day life, but the important thing to know when using this formula is that it's for gases. Boyle's Law is for gases, not for other things in our life. You can use any units for pressure and volume as long as they match so that they cancel out. And the last thing to know is, since Boyle's Law focuses specifically on pressure and volume, we want to keep other things constant. So we're going to keep the amount of gas, which is symbolized with an N. The N stands for moles of gas. We need to keep that the same. That can't change. Temperature also needs to be kept the same or kept constant when we're using Boyle's Law. Let's do this problem about helium gas that shows us how we can use Boyle's Law. When I'm reading through these problems, I like to focus on finding my matched pairs. So it doesn't matter who you plug in for P1 or V1, as long as they're part of the same set or same pair. So the helium gas has a volume of 2.0 liters. So I'm going to label that as my V1 at a pressure of 4.0 atmospheres. So that's going to be my P1. What is the volume of the gas at 5 atmospheres? So I have this second pressure, which I'm going to mark as P2. And then this is going to be V2 because it goes along with P2. But we don't know V2, right? That's what we're solving for. So we're going to use Boyles Law. P1V1 equals P2V2. So I'm going to do 4.0 atmospheres times 2.0 liters equals 5.0 atmospheres times my unknown, the V2. So you can do this all in one step in your calculator. You're going to put parentheses around these two things when you multiply them. And then since we're trying to isolate V2, we're going to divide each side by 5.0 atmospheres. Let's check how the units are canceling. So atmospheres will cancel with atmospheres, leaving us just with liters, which is perfect because we're trying to solve for V2. So V2 here winds up being 1.6 liters. Let's think about this. What happened to pressure? Well, pressure went up a tiny bit, right? Pressure went up from 4 to 5 atmospheres. When pressure goes up, we expect volume to go down. Did the volume go down? Yeah, because the volume started at 2 and went down to 1.6. So if I can, I like to do that quick mental check to make sure I didn't make an algebraic mistake or something like that. The next law I want to discuss is known as Charles's Law. Charles's Law tells us that volume and temperature exhibit a direct relationship. I want to show you something super cool. It's called a hand boiler. And it's actually a very fragile glass device, and it's got liquid ethanol in the bottom, and there's some food coloring or dye. That's why it's purple. So as I put my hand on the bottom of the glass, the temperature of the ethanol goes up, which causes the volume to expand, forcing the ethanol into the top of the glass sculpture here. And if I get it warm enough and if I hold it long enough, eventually all of the ethanol that was on the bottom goes up to the top. And it quickly reverses itself once the temperature drops. So I just find it really cool, really fascinating. But it's an example of Charles's Law at play. So again, the two exhibit a direct relationship. One goes up, the other one goes up as well. The temperature, when we do the math for this, the temperature has to be in Kelvin. We need to avoid Celsius because Celsius has negative numbers, and that might result in a negative volume. There's no such thing as a negative volume. So use the Kelvin system because that only has positive temperatures. And then the units of volume, you can do whatever, but they just have to match so that they cancel. When we're looking at Boyle's Law, we're talking about what do we hold constant. Here, we're going to hold pressure constant and the amount, or N, constant as well. Let's set up a Charles's Law problem together. So we have a 48.3 milliliter sample of a gas. I'm going to just arbitrarily call that V1. And they warmed it from 22 to 87 degrees Celsius. So here I have to think, who is T1 and who is T2? What is the volume at the final temperature? This is a key word here, the final. So if it's warming, the final temperature is going to be the 87. So I can call that final volume V2 if I put a T2 on the 87. So initially, or at first, it had a temperature of 21 degrees Celsius. So what I did here was I did 22 plus 273.15, and now I have T1 in Kelvin, and this is T2 in Kelvin as well. We're going to use the formula V1 over T1 equals V2 over T2. And what I want to show you about this, fractions for me have always been a little bit difficult to deal with. I want to kind of eliminate them as soon as I can. So when I see this relationship, say on my formula sheet or whatnot, I'm going to cross multiply so that I get it in a form that I feel more comfortable manipulating. So when I do that, when I cross multiply, I'm able to rewrite this as V1 T2, because I'm going on the diagonal, equals V2 T1. And now I don't have to worry about the algebra of fractions. Alrighty, and then we said V1 was 48.3 milliliters. Our T2 is 360.15 K. We don't know our V2, and our T1 is 295.15 K. So see how much easier that made everything since I already cross-multiplied? Now I know I need parentheses here. I'm going to plug that into my calculator like that. And I want to isolate V2, so I'm going to just divide by 295.15 Kelvin on both sides. Let's check how the units are canceling. That's always important. Kelvins are canceling with kelvins, and I'm just left with milliliters. So at the end of the day, I got a V2 value of 58.9. Last thing, just like we did in the other problem, we want to think about the simple gas law and if our answer makes sense. So we know volume and temperature are going to go in the same direction. Temperature went up, so volume should have gone up as well, which it did. So it's a nice, again, mental check to make sure we're on the right track. Same approach here. We're going to go through and label all of the things that the equation gives us. So we have a sample of gas. It has a volume of 2.80 liters. So I'll label this as a V1 at an unknown temperature. So that's an awesome clue right there. T1 is what we're solving for. When the sample is submerged in ice water at T equals 0 degrees Celsius, so that's going to be our second temperature, the volume decreases to 2.57 liters. So I'm going to call this one V2. Alrighty, so I went ahead and converted what we now know to be T2 to kelvins. It's a really important step for anything with gas laws. Make sure you're working in kelvins. The volumes, they both have units of liters, so we're good to go there. The only stipulation is that the units have to match. The other thing I went ahead and did is I did my cross multiplication. So now I have V1 T2 equals V2 T1. So let me start plugging stuff in. So V1 is 2.80 liters, and I need to multiply that by T2, which is the 273.15 Kelvin, and that's going to equal V2, which we know it's the 2.57 liters. It's so helpful to label this stuff. It helps me when I get confused. So, and then we don't know T1. So I'm going to do 2.57 liters times T1. We're trying to isolate T1, so I'm going to divide both sides by 2.57 liters. Then I'm going to check, see how my units are canceling. So liters will cancel with liters, which just leaves us with Kelvin. So that'll definitely work out. This goes away completely, right? So T1, when I solved for that, I got 297.60. It's actually 595, but I'm gonna round it. At this point, that would have units of Kelvin. Now, to convert from Kelvin to Celsius, instead of adding the 273.15, I need to subtract 273.15. And I know some of you might be concerned about the rounding rules. Did I cut off digits too early? I have the whole number in my calculator, so I recommend you do the same. Write down whatever you want, write down the correct number of sig figs, but keep the whole number in your calculator. So in Celsius, this would correspond to 24.45 degrees Celsius. So someone took this gas and they made it cool. So I expect, because temperature dropped, I would expect volume to drop as well. They have a direct relationship. Did temperature drop? Yes, temperature started at 24.45, dropped to 0, and then we also saw that our volumes dropped. Yeah, started at 2.80 and dropped to 2.57 liters. Again, highly encourage you to always just check that the simple gas law relationships are working out after you do your algebra. The next simple gas law that we have to go over is called Gay-Lussac's law. It relates the temperature of a gas to its pressure. So as temperature increases, pressure increases. The opposite is also true. If pressure were to decrease, temperature would decrease. They're directly related. They go in the same direction. You can see this law in play if you ever use an Instapot or a pressure cooker or something like that. So the Instapot, which are just pressure cookers rebranded, promise to cook food really, really fast. How does that happen? How does a stew that would normally take 4 hours now all of a sudden can be ready in 40 minutes? So the pot has a bunch of gaskets and seals. So you put on that top, and as it's cooking, the pressure is going to increase. The pressure is going to build up because unlike a regular pot where the gas just escapes, all the gas gets stuck inside that pot. So increasing that pressure increases the temperature that it boils at above 100 degrees Celsius. So water boils at 100 degrees Celsius, but if you increase the pressure, then you can get the water to boil and get to much higher temperatures, which then allows your food to cook faster. Pretty cool use of, chemistry. When we do this law, N and V are held constant. So the amount of stuff has to stay the same and the volume has to stay the same. Just talking about the Instapot, the pressure cooker, we see that. N stays the same because you don't add food in the middle of the cooking process when you use the Instapot. The volume stays the same because if you've ever picked up one of those things, it weighs a ton. It's got really, really thick walls that don't allow the pot to start expanding. Like if you increase other things, increase the pressure in a weaker device, it would start expanding to the point of an explosion. So that's what happens to like a soda can that you leave in your car on a hot day. It's gonna explode because the aluminum is not thick enough. But with the cooking devices, they want them to be safe. They don't want them to explode on the consumer. So the walls are thick enough that the volume doesn't change as the pressure is building up. It's going to be P1 over T1 equals P2 over T2. Do whatever you want with the pressure units. They just have to match. And as with all of our simple gas laws, the temperature has to be in Kelvin. So if you flip a couple pages ahead and go to number 5, we have an example of Gay-Lussac's law. So the pressure of gas in a tank, let's call this P1. And I also know it's pressure because of the units, right? Atmospheres is a common unit for pressure. Is at 22.0 degrees Celsius. So this will be my T1. If the temperature rises to 60 degrees Celsius, let's call this T2, what will be the gas pressure in the tank? So basically we're solving for P2. Already went ahead and converted the degrees Celsius to Kelvin. So we have 22, which is 295.15 in Kelvin, and this is my 60 converted. Remember, on our gas laws, we always have to use Kelvin. The relationship is P1T1 over P2T2. I'm going to use my trick of cross multiplying. So when I rewrite this, I get P1T2 equals P2T1. So let's plug and chug and start solving this. So P1 is 3.20 atmospheres. And we need to multiply that by T2, which is 333.15 Kelvin. And that's going to equal P2, which is currently unknown, times the T1. Big set of parentheses over here. Let's divide both sides by 295.15 Kelvin. Check my units. So Kelvin will cancel Kelvin, leaving me with atmospheres. And when I plug that in my calculator, I got 3.61 atmospheres. I left it at 3 sig figs because everything else was 3 sig figs. Always do that mental check. We know it's a direct relationship. Temperature did go up from 22 to 60. So did pressure also go up? Pressure started at 3.20 and went up to 3.61. So it looks good.